Uh, so can you hear me clearly? Hello?
Professor, can we start now or can you wait for another 5 minutes to start?
Oh, I can wait. So where are the participants? Are they in the break or they're?
They're on the way. After completing the lunch, they are coming back.
It's okay. I can wait for 5 minutes.
Yeah, please.
No,
Thank you.
no problem. Yeah. Okay.
Yeah.
Let me upload my slides. Okay, I need to find my slides. Hold on, okay. I'm looking my slides. Okay, okay. I found my slides. I'm gonna share my slides. Okay. Let me know if you can see my slides. Can you? Can you see my slides?
Visible, sir.
All right. I think yesterday, when I lecture, we are left out from here. So this is electrocatalytic process to make ammonia. So we continue the topic. Okay. Let me go back to. So topic is the overview of green ammonia synthesis. So how many methods we have in producing the green ammonia. So I think yesterday we went through microwave, we went through electrocatalytic, and then we talk about hydrogen evolution over the potential, and the advantage and also disadvantage of the electrochemical process. So today, let's continue. So there's another method to make the so-called the green ammonia. So you basically using the sunlight, it's so-called photocatalysis. So photocatalysis means you have the material which is photo. It's similar to the electrocatalytic process, but electrocatalytic process you use electricity, all right, and then you have the electrode, and on the electrode you have catalyst. It's really the artificial process because you have to make a catalyst, you have to have the something the battery to run the reaction. Photocatalysis, your energy coming from solar. Okay, so your energy coming from solar, but you do need have something like the either called the artificial leaf or the artificial material. They call the semiconductor. Semiconductor means it's sensitive to solar light, and then taking the water and make a proton, and then the proton react with the nitrogen. So it's kind of mimic the nature process, but because nature process is very slow, it depends on the plants. All right. So this one they are kind of make it artificial sunlight sensitive material. I don't want to go through the detail because a lot of the photo chemistry need to get involved. So in the interest of time, I only want to show you the different method to make ammonia. Okay. So the next method is called chemical looping. So before I talk about chemical looping, I want to show you a diagram. So this diagram, I think from a book. The book basically the publisher, hey, in ammonia synthesis, remember we say it's thermodynamically controlled. That means the reaction will never go to complete. So let me start writing the equation here. So let me show you. So on the left hand side, just thermodynamics. On the right hand side, kinetics. So let's only focus on the thermodynamics. What's the thermodynamics say? Okay. I'm gonna put it in here. So basically, you have nitrogen. Oh God, I don't have space to write this. Let me write down here. So you have nitrogen plus hydrogen, and make ammonia. All right. So basically, this reaction will now go to 100% completion. That means at any time, if you have a reactor, at any time you have a mixture of nitrogen, hydrogen, ammonia together. That means you will not convert the nitrogen 100 completely. So that's why this curve is already in the textbook. In textbook means they publish and put in the book. So what does this mean? Let's try. So this is the thermodynamic, the equilibrium curve. That means on the x-axis is the temperature, on the y is the ammonia concentration. So and each curve is the pressure, is a bar. So let's say the 0.1 is 0.1. This is ambient pressure, and the ambient pressure, I would say at 300 degrees C, you barely get like I would say probably 5% of ammonia equilibrium. So that's very low. So the lower the temperature, the better. Remember we talk about the thermodynamics. This is thermodynamics, not the kinetics. Kinetics on the right hand side. So if you go to 400 degrees C, and then at the ambient pressure, you don't get any, you will not get any ammonia. The reason being that at a low pressure, high temperature, the equilibrium will go to life. All right. So 400 degrees C, you get nothing, and 500 degrees C, ambient pressure is out of curve. What does it mean? That means if you run the reaction hydrogen, nitrogen, ambient pressure at the 500 degrees C, essentially you do not get ammonia because the moment you form ammonia is equilibrium. It's a move to the left. So basically, you really need to go to high pressure. The higher the better to get higher concentration ammonia. So in ammonia synthesis, you do need high concentration because you need to do separation, compression, and recycle. Okay, so this curve is you can find this curve in the textbook, and then it's a very famous book, the curve. So it's just talking about thermodynamics. I'm not going to talk about kinetics. So now facing the thermodynamic limitation, how would you break the thermodynamics? So there's a process called the chemical looping. So chemical looping is a way to break the thermodynamics. So what does for thermodynamics mean? Thermodynamics means if you have a vessel, okay, that's a black box. You have nitrogen, you have hydrogen, and you have ammonia. And the given temperature and pressure, they are going to reach equilibrium. Remember that? So I'm talking about thermodynamics means all three molecules has to present in one vessel at a given time. At a given time, under pressure and the temperature, I would say under temperature and pressure and a given time, and then they are reaching equilibrium. How would you break this equilibrium? Keep in mind, Nitrogen, hydrogen, the moment that you put in the same methyl, they produce ammonia, they reach equilibrium. They will never go to 100% at any given time. How would you break the equilibrium? There's a process called chemical looping. Okay, so let me ask I don't see too many students coming back. So whoever in the audience, have you ever heard of a terminology of chemical looping? I just want to know. I mean, not necessary for ammonia synthesis. Chemical looping can be utilized for combustion, can be utilized for any other reaction. But today I'm talking about chemical looping for ammonia synthesis to break the equilibrium control. Anybody in the audience can give a try? Have you ever heard of chemical looping? Any? Yes, go ahead. Yeah, if you. So just say that the terminology, see the title of this slide. So chemical looping. Have you ever heard of chemical looping? Because I'm going to go through the detailed equation on the bottom. Before I go to that chemistry, I want to know if you ever heard of chemical looping, so I can just talk about this loop. This is a very complicated process. Anybody just tell me yes or no? Yeah.
Metal oxides to convert into fluid and oxidize in a
Okay. So when you said about the converting to oxide, all right? So the so-called oxygen carry. Did you say the converting to oxide? All right.
Yes, the definition I don't know anything.
Yeah.
They are not aware of that terms.
You're not aware of this. Well, let me give you a basic theory, okay? So chemical, let me. So chemical looping for ammonia, before, since the audience has not talked about, have not ever heard of the chemical looping. So the whole idea of chemical looping is to break the equilibrium control. Okay, so this equilibrium control, we want to break it. So that means they are not subject to this curve. How we are going to break it? So let me give you the basic theory. So you basic chemical looping, you need some kind of carrier. Okay, so yeah, normally I think Dr. Anand, I lecture this for the audience of chemistry or chemical engineering. So I look this audience is very difficult to lecture because I have to tell a lot of basic theory in order to tell the method. But I want to slow down in order to, I mean, I don't have to rush. So I have this blank sheet talking to here. Chemical looping came from the combustion process. So let's say if you have if you want to generate heat, you have combustion. So basically, in any chemical plant, if you need what you call that heat, so you take the natural gas fired heater, you basically combust with the oxygen, and then you produce CO2 and water, and then generate heat. It is heat you need it, but the problem is that in the conventional combustion, you mix the methane and the oxygen together. It's not really oxygen; it's air. So when you have air, don't forget you have a nitrogen, all right? So when you do combustion, nitrogen will not be combusted. So that means you have the nitrogen in here at the end of a reaction, all right, plus heat. So but if you do the CO2 capture after combustion, so-called the flue gas, so the CO2 concentration is very low because the majority is nitrogen. So that means you have to capture CO2 and then concentrate CO2 to 100% in order to capture CO2. So that's a lot of work. How would you produce CO2 without capture? So the people invented the chemical looping process. Okay. So once you understand what I'm saying here, you will understand the chemical looping for ammonia. So this is called the conventional combustion. So let's do the what do you call it? Chemical looping. Chemical looping combustion basically means first what you do is you find a material which is solid with oxidizer. You react with this material, and then this material is oxidized. Methane react with this oxidizer. They form what? They form the carbon plus the iron. All right, make sense? So that's the chemical. So but the key is you have to have this the so-called oxygen carrier plus H2O. That's what they do. So and then by doing so, you basically generate heat. So this is basically the process. Now the next step, what you need to do is this is one step. Another step is basically called iron plus. Okay. Let me go. Give me 1 second. I need to go back to the another sheet. Okay. I want to show you a diagram. So this is easy to show in a diagram. So basically, I think I heard a student just say oxygen carrier. Instead of a combustion molecule, you need an oxygen carrier. Okay. So then you plus the air. And, let me go. I'm gonna go and grab another cartoon. So you know what? It's better illustrated using the cartoon. Okay. Okay, give me 1 second. Coming, copy. Okay, I think I'm coming back. Let me share the slides again. Yeah, this for my the current class. Can you see my slide?
Yes.
Okay, so this is basically it's an illustration of a chemical looping process. So remember the conventional process. The conventional process combustion process means you have the methane reacted with air, oxygen, and then produces CO2, and then water, and then but nitrogen stay in there. Okay, when nitrogen stay in there, they create a problem because of they dilute CO2. So oxy combustion is running in such a way. They separate the process into two vessels. Okay, so but they use oxygen carrier. Oxygen carrier means it's a solid. So basically, instead of burning methane in one vessel, they basically circulate this oxygen carrier in two vessels. So what does it mean? That means methane and oxygen, they do not see each other. So now I come back to this graph. So keep in mind, here methane and oxygen, they see each other because you use air, then the nitrogen the present in the combustion, the flue gas, and then CO2 get diluted. Is a problem. So how do you produce the CO2 100%? So you have to use an oxidizer called the oxygen carrier. So first you react methane with oxidizer, not O2. Okay. So then you produce CO2. There's no nitrogen here because methane react only with this oxygen carrier from the iron metal. Then you turn around having iron react with air, which is O2 plus N2. So then they oxidize into the Fe2O3. Make sense? All right. So now you recover this oxygen carrier. So back to this loop. So on this side, it's basically methane reacted with the oxygen carrier from the CO2. This CO2 is a pure CO2 because air doesn't come to this side. Air coming to the other side when the metal oxide and going into the other side and then react with air. So I can send you this slide and you can do the Google. You see the chemical looping process means if you use two vessels having oxygen carrier, and then you can produce the CO2 without the nitrogen because nitrogen actually is on the other side of the reactor. So now the same concept, since the audience has not heard of this, I'm not going to go through this oxy combustion. It's pretty popular in the United States for last 20 years. Now I think that it's kind of the cooling down because there are some other issue of the engineering issue. Basically, you have to circulate a solid oxygen carrier around. So now in the ammonia synthesis, we use the same concept, the chemical looping. You have two vessels here, but this time it's not oxygen carrier, it's a nitrogen carrier. Okay, so I want you to see this is the equation. Let me turn into the presentation mode. So when I turn into the presentation mode, and then I have this. So this is the equation. So essentially, you have the metal, and then react with the nitrogen to form the metal nitride. It's the same as the oxygen carrier. This is nitrogen carrier. You need a solid, and then this the metal nitride, and then react with the hydrogen to form the ammonia. So let me back to my equation. There should be another equation on the bottom here. So anyway, so this is basically the loop. One loop is you have the nitrogen reacted with metal to form the metal nitride, and then in another loop you have hydrogen reacted with metal nitride. So in this case, hydrogen and nitrogen, they do not see each other. So the reason you have equilibrium in ammonia synthesis because you have hydrogen, nitrogen put in the same vessel at the same time. By doing the chemical looping, hydrogen, nitrogen, they are in different reactors, and they never see each other, and then but they react at a different time. You follow me? So you use the space and the time to segregate this reaction so that they are not subject to equilibrium. So this is the way how you break the so-called thermodynamics. I'm not sure if you understand the concept. So traditionally, the ammonia synthesis subject to the equilibrium control, you follow this curve. There's a way you can break this curve by doing the chemical looping. Make sense? I'm going to pause here. I just want to know if anybody has any questions. It's a very complex process. I can talk about chemical looping for hours, but here I want to show you at a very high level. This is one way to make ammonia. This is not my focus of my lecture today or for the session, because it's so much detail you have to go through. Actually, I have a student, PhD student, graduate. He actually published several papers using this chemical looping, microwave plasma chemical looping process. Okay. Any questions?
Yes, sir.
Go ahead.
In chemical looping, there is some methodology to produce ammonia by through chemical chain method. I think I heard about that method long back.
You heard the method. Thank you. Yeah. So it's the same as the oxygen carrier. You need what you call that, a nitrogen carrier. So that's why this equation on the bottom. You have to select a metal or metal complex reacted with the nitrogen, forming this complex. It's called Mn. Mn means metal, N means nitride. It's not the N2. So by doing so, you activate N2, but N2 bonded with the metal. You follow me? But you have to release it. When you release the metal, you react with hydrogen. That's chemical looping of ammonia. So is that do you have a question, or you just say you heard about the chemical looping of ammonia?
Yes, sir. One small question. If oxygen or nitrogen obtained from metal, which are metal oxides or metal nitrates, then we call that as looping, or is there any other general definition for chemical loop?
Yeah, there are some other no. In this case, for ammonia synthesis, you have to use the pure nitrogen. There's no oxygen involved. In oxy combustion, in this case, a chemical looping for combustion, you can use the air. You don't have to use the oxygen. You follow me? So I couldn't catch exactly what you are saying. In chemical looping, for ammonia, you have to use a pure N2. There's no air in here, so you have to do separation. The key here is that the metal has to react with the N2 to form the metal nitride. You follow me?
Yes, sir. If previously we said methane react with metal oxide, then we will get carbon dioxide and hydrogen plus.
Yeah.
Is there any heat from that reaction?
Yes, that's oxidation. Yes, you are talking about this reaction. So basically, in this, yeah, thank you for the question. Yeah, there's heat. There's heat coming out. Yeah, this oxidation reaction. Basically, you have you can look at the equation from the energy balance point of view. You have the methane carry energy. You have metal oxide. Let's say on the right hand side there's no energy. There's a big energy level is 0, 0, 0. That means in order to balance the equation, you have to have heat coming out. Energy balance. Will you follow me? Yes, there's a lot of heat coming out. So this is the way to generate heat, but the heat is coming using the metal oxide. So I think your question will be how you are going to release combustion. Heat is a so-called radiate, right? When you combust the air, the vessel has heat convective coming out. Here, heat will be carried in the solid. A lot of heat coming out. You do heat changer to utilize the heat. Did you get that? Did I answer your question? Yeah, there are a lot of heat coming out.
Yeah, yes, sir, I got it. Whether heat is coming or not, that is my question. Actually, I got the answer.
Well, could you repeat your question again? Yeah.
I got the answer, sir. Actually, chemical looping combustion also will give heat.
Yeah.
Yeah.
Chemical looping combustion equally release the heat, the same as conventional combustion. Because I mean, if you do the balance, it's the same thing as in here. So basically, here you heat coming. If you do the energy balance, you heat essentially coming from the methane, natural gas, all right? Because the rest of this doesn't have any heat coming out. So same with methane in the chemical looping, the heat coming out as well. So on this side, there's no heat involved. Here, the release a lot of heat coming out from this side. Even on here, when you oxidize oxide iron, there's also heat coming out. So by adding these two equations together, the heat equivalent, the heat from chemical looping is the equivalent heat here. I think that's your question. Hold on. So let's call it heat 1.
Yeah, yes, sir.
Let's call it heat 1, and let's call it heat 2. Let's call it the plus heat 3. So basically, it's the same. So the heat 1, I'm sure you understand what I'm saying. So heat 1 equals, oh God, what's going on with my computer? Equals heat 2 plus heat 3. You follow me? Heat 2 and 3 are chemical looping. It's the same. All the heat is coming from the methane combustion. So chemical looping, if you're adding the two heats, because you generate heat separately, you add the heat together equal to the conventional combustion. Make sense?
Yeah, exactly. Yeah,
yeah, this is energy balance. So same with the ammonia, but the downside, that's why I have so many slides in here. I don't want to waste time. I want to basically present high level the knowledge to the student. And if I go through this, there's no end for today. So that's why I say that the high level, if you add balance energy, chemical looping basically release the same amount of heat as the conventional combustion, just how you manage the heat in the two vessels. Yeah, it's engineering issue. Okay. Yeah, so that's why I didn't enter into the discussion on advantage and disadvantage. There are a lot of disadvantages, but advantage is you produce the pure CO2. Here you save the capital because you don't have to capture CO2 because CO2 never see nitrogen. And then, well, by the way, nitrogen is here. Nitrogen is in the second vessel. But here, since you put the methane and air together, CO2 and nitrogen, they combine together. So in the chemical looping combustion, you do not need to capture CO2. You just use the CO2, pure CO2, because it's here. Make sense?
Yes.
And okay. All right. So let's continue on. Yeah. Thank you for the question. So I'm continue this topic. The different way to make a green ammonia. So this is the way to make a green ammonia. Basically the chemical looping approach, same as oxygen combustion. We use the nitrogen carrier. You can, by doing this looping, you can break the thermodynamics. And by the way, this is ambient pressure operation. So if you look at ambient pressure operation, I'm going back. Keep in mind, ambient pressure operation 400 degrees C, you essentially do not produce ammonia. But chemical looping ammonia synthesis, you have to operate at 600 degrees C. And I can email, I think I can email Dr. Anand the paper from my student. And then, but if you look at this conventional way to make ammonia, 600 degrees C ambient pressure, you do not produce ammonia. But that's not true. When you do the chemical looping, you are not subject to all of this because this thermodynamics means in a sealed vessel, hydrogen and nitrogen putting together is subject to this. If I separate the hydrogen and nitrogen, all this curve doesn't apply anymore. So this is a very good innovation on the ammonia. There's so many papers published in the Science and Nature in there. Okay. All right. So let's go to the next process. Next process is plasma. I think Dr. Anand, I know this is before me, Dr. Anand also mentioned about the plasma. The different way to run the plasma. So there's to make the ammonia. So why you run the plasma? So plasma basically is, I think in day one of the students mentioned about the lightning. Yeah, lightning is kind of plasma because you pre-activate the molecule and then they react. So this cartoon really shows how they run the plasma reaction. So the plasma reaction means it's called the DBD, the packed by the DBD. So you apply the voltage and then you pre-activate nitrogen and hydrogen. I'm going to write a chemical equation to you so you can see it. So basically the plasma, let me borrow the equation from. I'm talking about the plasma chemistry, okay? Where's my? So if you look at the conventional reaction, it's more like this, okay? So this reaction takes the high temperature, high pressure, and thermodynamic control. The reason you want to run the high temperature because of kinetics, all right? So I'm trying to draw a diagram. Okay, so let me draw a diagram here. So it's basically N2 and H2. And there's ammonia. Has anybody heard about the activation energy? Just say something. It's called activation energy.
Yes, sir.
So if you ever heard of activation energy, so basically you have nitrogen and hydrogen. The reason you need to heat it up because at room temperature they are not right. So you have to heat it up because the molecule need to be activated, overcome this the mountain. It's called activation energy, and then you're passing through here. So without a catalyst, this is very high. This is called this is mountain. So now with the catalyst, go here. So it's no catalyst. I'm sorry, this is very difficult to write. Okay, so catalyst I just abbreviate no catalyst. So this is going to be with cat. Okay. So with catalyst, it goes here. You lower activation energy. That's the whole idea of the ammonia synthesis. You use the catalyst. Now with the plasma, you basically you don't change the here. You don't change it here. The plasma actually you activate the molecule instead of starting from N2 high H2. You actually turn N2 into N2 star. It's activated. Basically, you kick out electron. And then either become N2 star or N2 minus. And the same with the hydrogen. So hydrogen become either the positive or negative charge. Okay, they carry the charge. So by doing so, it's not your starting point. It's not N2 H2 anymore. Your starting point is here. So starting from here, that means they take less energy to passing through this hurdle. So from the activation energy point of view, but it's true, you pay the price. You pay the price of using the plasma to elevate this molecule energy from here to here. But once you start from the plasma, it's easy to climb the mountain. Make sense? So this is very complex. I mean, it's easy for the engineering student to understand this is the flow diagram, but I've interpreted this from the chemistry point of view, how you overcome activation energy, all because of this the writer. Okay, so in this writer, so-called DBD writer, you apply the voltage. This voltage actually activates the nitrogen and hydrogen. So nitrogen and hydrogen is not in the original the neutral state. They are in the plasma state. That means either they kick out electron or they basically accept electron. So in the whole system, there's the electron, there's the iron, there's all kind of species. And then those species, if you calculate the energy, state, they are elevated. When they're elevated, it's so easy to passing through the mountain. So that's why that's a different way to activate the molecule. Anybody has any questions so far? I'm going to stop annotation and I'm stop here. I have to go back. Anybody have any questions? There's different way to using plasma to make. I have so I think I have a section to talk about plasma, but I think today I'm going to give you the high level how the plasma is taking place. By the way, the different way to generate plasma. You see the DBD writer. DBD is cold plasma. Cold plasma means if you have a molecule, so if you generate plasma, there's an electron, there's an ionic body. The electron is small, but the electron is very hot. But the remaining molecule is cold. That's called someone calls it a non-thermal plasma, someone called cold plasma. Cold plasma means the majority of a molecule, which is the ionic body, is cold, but the hot electron temperature very high, can be 1,000 degrees C. Yeah. So that's why the plasma direction is so reactive. And it's more like lightning. When you have lightning, you see the nitrogen activate in the air. But this is really artificial so-called activation using the high voltage. Yep. Make sense? So let's continue.
Yes.
Any question? Okay. If you don't have any question, I'm going to continue. Okay. All right. So keep in mind, this is another way to make the ammonia. A lot of literature talking about low temperature synthesis of ammonia. When you see the thermodynamic curve, you see ammonia thermodynamic, ammonia is a favor, right? So I want to keep on reminding this curve. So you basically see this curve, low temperature is a favor. You have higher ammonia concentration. It's all about, but the low temperature, kinetic is slow, right? So you need a super active material, either catalyst or material to active nitrogen in order to operate at low temperature. Otherwise, it's very difficult. But chemical looping is different. Chemical looping doesn't subject to the thermodynamics because they break the thermodynamics. So if you still believe you are subjecting to the thermodynamics, you have to find a material to run at low temperature. So this is another way to look at this this problem. So plasma is different. Plasma pre-active with a reactant and then make it reactive. So there's another way you can. This basically I cut and paste from the literature. That's why every page I show this will give you the warning. If you try to publish this, make sure you find the original literature and then get a copyright. Otherwise, if you publish, somebody will come after you. So, but for the classroom illustration, it's fine. As long as you don't publish, it's okay because this is other people's work. This one I cited from the literature. So basically, this low temperature ammonia is called perovskite, and I'm sure you heard about perovskite. Okay, perovskite is a kind of metal oxide, mixture of metal oxide deficient on oxygen. That's called perovskite. So they use perovskite to activate the hydrogen and nitrogen. Keep in mind, traditional way to make ammonia, the high temperature, high pressure catalyst, put in the one high pressure vessel, they let the nitrogen and hydrogen see each other, and then subject equilibrium. So the whole industry or the research field, they try to break that hydrogen nitrogen. They want to pre-activate nitrogen and hydrogen by all means. What does it mean? You can use a plasma, you can use a material. So this is a good example. They develop this material, they call the barium oxide, and then the pre-react the nitrogen and hydrogen to make it is a mixture of nitride and hydride. Keep in mind, it's not N2H2 anymore. It's NYHZ. So basically, the bond already breaks. The way they break the bond is they react with a solid perovskite. So let me repeat. This is the perovskite complex has a lot of vacancy. Those vacancy allow nitrogen come in, become nitride, and allow hydrogen come in, become hydride. Now, once you become nitride hydride, then the reaction take place. So they basically using this is more like a shuttling effect. Shuttling effect means they have a material absorbing nitrogen and hydrogen, having them break the bond, then they release them into ammonia. So keep in mind, and then nitride and hydride in this material is not ammonia. It's bonded with this complex. It's still nitrogen, but it's called a nitride. It's hydrogen hydride, but it's not H2N2 anymore because bond already broke. So on the right-hand side, it shows you the cartoon. So once they broke the bond, then they try to have the react on the surface. When they react surface, when they recombine, nitrogen will now go back to find the nitrogen. Nitrogen will find the hydrogen to form the ammonia. So this is really very complex mechanism. I hope you understand the chemistry in here. So basically you form nitride and hydride. So when nitrogen and hydride form on the surface, they find the counterpart. Nitrogen find the hydrogen. So if nitrogen find the nitrogen, they will go back to the N2, all right? If hydrogen find the hydrogen, they'll go by H2. That's possible. But the key is you want to enable nitrogen and hydrogen on the surface to make this ammonia. I'm talking about on the upper right the corner. I'm gonna stop here, and anybody have any questions? This is very complex, the chemistry. So this, but it's another way to make the ammonia. Actually, there's a Japanese group and try to commercialize this. I invited this group in the American Chemical Society, give a lecture. Oh, they developed this material. This material very expensive. So and this is ambient pressure, and then ambient temperature is only 40 degrees C. So remember, hyperbaric 500 degrees C, 250 bar. They can do this in 1 bar, 40 degrees C. So the downside of this will be you have to use this super expensive reactive material. So I mean, any the chemical processing, if you want to do innovation, it's not going to be free. All right. So you reduce the temperature, you do pressure. What the price you pay? You pay economic price, basically this material. But yeah. So I think they published this paper in the Nature. Any questions before I move to the next?
This nitrate and citrates also coming under chemical looping. I want to know.
Yeah, this is similar. This is similar to chemical looping, but it's not quite. Chemical looping, you need 2 reactors. Here, you need 1 reactor. You follow me? So basically, this is like a continued process. You have nitrogen and hydrogen coming in. I basically disconnect and segregate the process for you. So you have this material, either you call catalyst or you call nitrogen and hydrogen carrier. So nitrogen and hydrogen come in, they react, and then you basically in the same reactor you heat it up, but keep in mind they react and at a low temperature. See the title, at low temperature. So now you heat it up in the same reactor without moving a solid, and then nitrogen hydrogen combine. It's similar to chemical looping, but you do not need to move the solid around. Chemical looping, remember, you have to move other material around. Let me go back to the chemical looping. See the chemical looping, you have to move this material around. You need 2 reactors. Here, you only need 1 reactor, but 2 different time. That means low temperature, then you raise the temperature, and then this is the surface nitride, surface hydride, they are going to react each other. Good, very good question. Make sense? Yeah, I think you can say they borrowed the concept from chemical looping, but they are more complex than the chemical looping because the unique of this the process is this material. Look at this how complex the material. I'm not sure. I have a PhD student. I have my PhD student try to make this material. It's just so complicated. So that's why my PhD student basically going back to this process. So you use microwave plasma, but we have a simple metal nitride to make this looping, and rather than going through this complex. Good. So I know we have a couple minutes before break. Let me finish this. Next session, I'm going to talk about the whole session about the microwave, okay? Microwave catalysis. So I think I'm almost done for this. All right. So there's another process. Basically, it's also electrochemical, but they use the different material in there. It's called electrochemical ammonia cell. So this cell, instead of connect to the battery, they can connect directly with renewable power, which is good. So most of the electrochemical process in the laboratory, even if they claim, oh, I can use the renewable energy, but in a laboratory they just use the battery as the power to supply the fuel cell. Okay, so they never even connected to the solar and the wind. But there's a group, they basically develop this cell, but they're using the different material, using lithium mediated system. It's really battery. Just the battery, basically they produce the ammonia. So the key is the lithium. So if you're familiar with inorganic chemistry, same with the perovskite, lithium can activate the nitrogen. You see the nitrogen coming in and reactive with the lithium, and then they basically they form the the ammonia, but the whole system is driven by the renewable power. So I think someone, if you do the Google, you can find this group, and then you use the keyword electrochemical ammonia cell. So this cell has the electrode, and then they're using the lithium to activate the nitrogen, and then but they connected the cell to renewable power. I think this is a very good group. I've been talking to so many research groups around the world. Everybody claim renewable power. Nobody actually connect to renewable power, but they sell this the whole assembly in there. So anyway, I just tell you, it's same electrochemical, but directly connect to the renewable power. All right, so last slide for this session. And so there's I think in day one, we talk about the so-called biological process. You can mimic a plant, or you can basically do the simulate the nature to make a material called the nitrogenase enzymatic process. Enzyme. So what's the enzyme? Normally, during the in-person lecture, I ask the audience, but in the interest of time, I'm not going to ask them. I'm going to answer my question for you. So the enzyme is a biocatalysis. Okay, enzyme is basically a protein, and then basically you can make this protein enzyme enable to activate nitrogen. You can do artificial. You can find this in the nature. So but typically the nitrogenase, which is a catalyst, if you find in the nature, they are really not very reactive, because their job is just to be stable in the nature. They don't really care about the kinetics. But if you want to produce ammonia faster in the laboratory, you have to engineer this enzyme. All right, there's a way to engineer enzyme because it's a protein. You can do the DNA. So I don't want to do that. There's a lot of the biochemistry group. They basically they do a lot of engineering work, enable this enzyme so that they can activate nitrogen. And by the way, enzymatic catalysis is very precise, because the enzyme, all right, is different from the other catalysis. Other catalysis, you always have a byproduct. But the enzymatic, you have one enzyme only do one job. Their job is to activate nitrogen. They do not activate anybody else. So I'm going to share. I don't want to go through the detail. I want to share you. There are some another method, enzymatic method. You can make ammonia, but you have to engineer the protein. Okay, so I think it's about the time to take a break, 30-minute break. So when we come back, we are talking about the next topic is microwave catalysis. So actually, that's the main research my group has been doing for the last 8 years. Should we take a break for 30 minutes now? Is it about the time for the break or the?
Yes,
yeah,
sir.
I think so.
Time
Yeah.
for.
All right, so let's take a break, and then we come back in 30 minutes. Okay. Right.
Sure, sir.
Yeah. Thank you, everyone.
Thank you, sir.
Cheers.
We'll have a break.
So the